Hey guys, Mr.Cram here. Are you feeling judged? Well, you should, because you're looking at Themis, who is an ancient Greek titaness, which is a great title, who was looked at as the divine judge. She was looked at as the perfect judge, and her opinions were valued for that. So you've probably seen this kind of statue before. We call it blind or justice, Lady Justice, and often you'll see her depicted as blind in front of courthouses or in the judicial system in the United States, but it's used actually all over the world. So the reason I wanted to show you this is just to get the visual of her balance, right? So her balance is used to judge whether a person, or really it was more about support versus opposition against a defendant, and whichever way the scales tilted, a person was either found guilty or not guilty. So we're going to talk about balances today. In chemistry, we're going to talk about it in relation to balancing chemical equations. A little bit different, but that's a nice visual you can hang on to. So in chemistry, why is this important? Matter cannot be created or destroyed. We'll talk about more of that statement in a little bit. It's a really common one you hear. Sometimes the word matter is replaced with mass, but it's going to tie into balanced chemical equations. And you should know that a balanced chemical equation shows how reactants change into products, but the amount of each atom remains constant, meaning we're not going to take away any atoms or get new atoms. We're just rearranging them. You can really think of it like playing with Legos, essentially. So the image here below shows you an unbalanced equation where we have two of these blue, which are supposed to be silver, atoms on the left side and only one on the right, as well as two of the orange oxygen atoms, but only one on the left. So they are not balanced, meaning we have different amounts on the two sides of the beam. Down below, we do have a balanced equation where the same amounts are on both sides. So that's what we're talking about. Alright, so in order to understand how to balance an equation, we need to know the parts of a chemical equation. So here's a quick review of all the different pieces. So there's the left side of a chemical equation. We say that's the reactant side, right? Those are the things you mix together to react. And then there's the product side, the things you produce. They're separated by an arrow or a yield sign. Pluses mean reacts with on the reactant side. If there's pluses on the product side, that just means you're making multiple things. And then finally, there's some numbers, right? So there are the small little subscripts, which tell you how many individual atoms are in a compound. But then the big numbers are the ones we're going to be dealing with today. Those numbers are called coefficients, and they tell you how many of a particular molecule you have. So here this reads 2 molecules of hydrogen reacting with, if there's no number, we interpret a 1. 1 molecule of O2 producing 2 molecules of H2O. And we have a balanced equation. Alright, so here's the same equation. I'm going to take you through the steps now of how to do this in the kind of visual way that I like to use, and we should get the same answers we just saw in the last slide. So whenever you have an equation, to determine whether it's balanced or not, the first thing you want to do is just start counting. So I'm going to start here looking at the reactant side, and I look at my coefficient. There's nothing there right now, so I interpret that as a 1. The 2 means there's 2 atoms of hydrogen, right? So I'm going to draw a little circle here in red. There's 1 hydrogen atom and 2. Okay? I'll use a different color for oxygen. Let's use blue. Again, 2 blue circles here represent the 2 oxygen atoms. So far, so good. Over here, I'm going to go back to red for my 2 hydrogen red atoms. That's what the 2. The 2 only belongs to hydrogen here, though. I interpret this as a 1 for oxygen. So there are my initial pieces, right? And quickly, you can probably recognize there are 2 hydrogens on the left, and we can kind of keep this as a dividing line here. 2 hydrogens on the left and 2 hydrogens on the right. That's balanced. That's what you want. But as you look at the oxygen, it's not balanced, right? There's 2 here, there's only 1 here. So we got to put numbers. We can never change the subscripts. We can put numbers in front, the coefficients, right? So if I put the number, let's put the number 2. on 2. There we go. Alright, so now what this means is 2 H2O molecules, so I can actually just multiply my coefficients by the subscripts. 2 times 2, 4 hydrogen atoms. So now I have 4 dots. And then 2 times 1, or 2 oxygens. Alright, so oxygen got balanced by putting that 2 there. Great. But by doing so, I changed my hydrogens. So now my hydrogens are not balanced. So I need to do one more thing. I need to put a 2 here. And now 2 times 2 will give me 4 hydrogens on this side. And when we're all done, we double check. Yep, I got 4 hydrogens here, 4 there, 2 oxygens, and 2 oxygens. I'm balanced. And that's how you want to do this, guys. You want to go back and forth by changing coefficients to make sure you get the same number of each type of atom on both sides. Alright, so a little bit more challenging this time. A little bit more stuff to keep track of. Why don't you pause it, give this one a try, and then you can see my work and check your work. Alright, so here, just quick visually inspecting what's going on. I'm going to see that there are 1, 2, 3 different types of atoms, so I'm going to want to use 3 different shapes or 3 different colors to represent those. So I'll start with carbon. Carbon, I have how many? I got 2. So 1, 2. Hydrogen, I got 4. Hydrogen will make blue. So I'll put 4 little circles in, blue ones. And then oxygen will make green. 1, 2. Go over to the other side. 1 carbon, 2 oxygens, 2 hydrogens, and 1 more oxygen. Alright, so here's my dividing line again, right? So now I can start balancing. I highly suggest you start with carbon and then go to hydrogen and save oxygen to the last. He's usually the hardest guy to balance. So here we go. Carbon, we got 2 here and 1 over here. So I can put a 2 there, and that will give me 2 times 1, or 2 carbons, and balance my carbons out. But it also changes my oxygens connected to the CO2. So 2 times 2, now I have 4 total oxygens here. So carbon is balanced now. That's great. Let's go to hydrogen. We got 4 here. We got 2 there. So what number makes sense? I think a 2 makes sense. 2 times 2 gives me 4 total hydrogens on this side. And then oxygen is going to be 2 times 1, or 2 total. Notice I didn't add 2 more, right? That's a common thought process that people make mistakes on. You actually just want to multiply the coefficient by the subscript every time. You'll get it right. So 2 times 1, 2. So now our hydrogens are good. Carbon's still good. Oxygens now. We got 1, 2, 3, 4, 5, 6 on this side. I got 2 on this side. You might be able to quickly think, all right, what number makes sense? 3 times 2, that gives me 6. So there we go. We now, the last step, you want to go back and just double check, make sure everything is in fact balanced. 2, 2, 4, 4, 6, 6. Make sure you count, even though they're on different compounds, all the atoms on the side are what you're interested in. You want the same amount on both sides. Doesn't matter who it's connected to. Okay? So we're balanced. Alright, so what is this law of conservation of matter, or this matter cannot be created or destroyed, right? What does that really mean? Well, it has something to do with the fact that, all the atoms in the universe have been around since the beginning of time. They've just been mixed up and changed into new things. You're, as the poets say, star matter, right? So when you look at this, this is a nice example of an experiment and how you want to think about this in chemistry class when a reaction's happening and you're seeing this macroscopic change going on. Maybe you see bubbles or color changes or solids forming from 2 solutions. That looks awesome, right? And it makes you think, wow, I'm creating new stuff. And in fact, you're getting new things, but the amount of atoms is not changing. And it's hard to wrap your mind around, right? So let's look at this example. Here we have a flask that is capped, and that's important. It's closed, so no air or particles can go in or out of this flask, right? So it says there's silver nitrate, AgNO3, in this test tube in here, and then we have a sodium chloride or salt solution below, and then we're mixing, and a reaction is going to happen between the sodium chloride and the silver nitrate. That's what's down here. And we're getting new stuff. We're getting silver chloride and sodium nitrate. And it says here that silver chloride is a white precipitate, or a white solid. And you would see that visual solid forming in this solution. So even though it looks like we're getting matter, some solid, right? It's not, in fact, new atoms. We're just rearranging them to get a new thing, a new substance. That's the silver chloride. So if you look at the mass here of everything in this, well, we'll call it a system, right? So the silver nitrate, the sodium chloride, the flask itself, we have 300.23 grams, right? After the reaction, what do you think, guys? What's the mass of our system going to be? Did it go up? Did it go down? Stay the same? Well, if you understand what this law is trying to tell you, you should recognize that the mass should be the same, right? Now, maybe it changes by 0.1 or 0.2 grams. That's not significant enough of a change, and that's commonly what you will see in lab. So be careful with that. Don't trick yourself thinking, well, it isn't exactly the same. There is a level of significance here. So, yeah, the masses should be exactly the same for before and after. Matter is not created or destroyed. All right, finally, one skill that you will become very good at this year is by taking word equations and turning them into balanced chemical equations. So here's an example of that. 1 molecule of nitrogen gas reacts with 3 molecules of hydrogen gas to form 2 molecules of ammonia gas. You should start thinking about, how do I represent that in a chemical equation? How do these numbers 1 and 3 make it into the equation? Okay, so here's my question to you first is, does the word equation above describe a balanced chemical equation? It could just be saying you mix these things together and you get this. It's your job to figure out if it's a balanced chemical equation or not. So here's how you want to think about this. All right, we'll read the first line again. 1 molecule of nitrogen, what is that going to look like in an equation? Well, N2, remember nitrogen is one of those 7 diatomics, and 1 molecule means that we would have the coefficient of 1 here, or no number at all, right? Because we assume the 1 is there. So there's my first reactant. Reacts is a key word there to tell me it's a reactant. And what's it reacting with? 3 molecules of hydrogen gas. Okay, so I'm going to put a plus sign. Reacts with 3, that's my coefficient, of hydrogen. And hydrogen is also one of those diatomics, those 7 diatomics. Then it says to form. That's telling you yields. How many molecules? 2 molecules of ammonia. Ammonia is NH3. So there's our equation. Is it balanced? Well, we can make the dots and figure it out, right? So 2 dots here for nitrogen. 3 times 2, or 6 dots for the hydrogen. And then we go to the other side. 2 times 1, 2 nitrogens. 2 times 3, 3 hydrogens. Are we balanced? Sure enough, right? 2 nitrogens on both sides, 6 hydrogen. So what should you have learned in this video? You should have learned how to identify the parts of a chemical equation, including what a coefficient and a subscript is, how to balance a chemical equation using the dot method, how to balance a chemical equation that supports, or how a balanced chemical equation supports this law of conservation of matter, saying that matter can't be created or destroyed, and then finally, how to write a balanced chemical equation from a word equation. Hope that was helpful.